Now, so far, I've talked about a lot of explicit labeling. So, like I mentioned, we ask people to annotate data. This is an expensive process in time and also with respect to, yeah, it's just an expensive process. And so these annotations, of course, can be very expensive to achieve. So what I want to talk about also is really to utilize the power of the fleet. You don't want to go through this human annotation bottleneck. You want to just stream in data and automate it automatically. And we have multiple mechanisms by which we can do this. So as one example of a project that we recently worked on is the detection of cut-ins. So you're driving down the highway, someone is on the left or on the right, and they cut in front of you into your lane. So here's a video showing the autopilot detecting that this car is intruding into our lane. Now, of course, we'd like to detect a cut-in as fast as possible. So the way we approach this problem is we don't write explicit code for, is the left blinker on, is the right blinker on, track the cuboid over time and see if it's moving horizontally. We actually use a fleet learning approach. So the way this works is we ask the fleet to please send us data whenever they see a car transition from a right lane to the center lane or from left to center. And then what we do is we rewind time backwards and we automatically can annotate that, hey, that car will in 1.3 seconds cut in front of you. And then we can use that for training the neural net. And so the neural net will automatically pick up on a lot of these patterns. So for example, the cars are typically yawed. They're moving this way. Maybe the blinker is on. All that stuff happens internally inside the neural net just from these examples. So we ask the fleet to automatically send us all this data. We can get 500,000 or so images. And all of these would be annotated for cut-ins. And then we train the network. And then we took this cut-in network and we deployed it to the fleet, but we don't turn it on yet. We run it in shadow mode. And in shadow mode, the network is always making predictions. Hey, I think this vehicle is going to cut in from the way it looks. This vehicle is going to cut in. And then we look for mispredictions. So as an example, this is a clip that we had from shadow mode of the cut-in network. And it's kind of hard to see, but the network thought that the vehicle right ahead of us on the right was going to cut in. And you can sort of see that it's slightly flirting with the lane line. It's sort of encroaching a little bit. And the network got excited, and it thought that that was going to be cut in. That vehicle will actually end up in our center lane. That turns out to be incorrect, and the vehicle did not actually do that. So what we do now is we just churn the data engine. We source that ran in the shadow mode is making predictions. It makes some false positives, and there are some false negative detections. So we got overexcited and sometimes we missed a cut-in when it actually happened. All those create a trigger that streams to us, and that gets incorporated now for free. There's no humans harmed in the process of labeling this data. Incorporated for free into our training set. We retrain the network and redeploy the shadow mode. And so we can spin this a few times, and we always look at the false positives and negatives coming from the fleet. And once we're happy with the false positive, false negative ratio, we actually flip the bit and actually let the car control to that network. And so you may have noticed, we actually shipped one of our first versions of a cut-in detector approximately, I think, 3 months ago. So if you've noticed that the car is much better at detecting cut-ins, that's fleet learning operating at scale. Yes, it actually works quite nicely. So that's fleet learning. No humans were harmed in the process. It's just a lot of neural network training based on data and a lot of shadow mode and looking at those results.
Yeah.
Another,
essentially, like everyone's training the network all the time is what it amounts to. Whether autopilot is on or off, the network is being trained. Every mile that's driven for the car that's hardware 2 or above is training the network.
Yeah. Another interesting way that we use this in the scheme of fleet learning, and the other project that I will talk about, is path prediction. So while you are driving the car, what you're actually doing is you are annotating the data because you are steering the wheel. You're telling us how to traverse different environments. So what we're looking at here is some person in the fleet who took a left through an intersection. And what we do here is we have the full video of all the cameras, and we know that the path that this person took because of the GPS, the inertial measurement unit, the wheel angle, the wheel ticks. So we put all that together, and we understand the path that this person took through this environment. And then, of course, we can use this for supervision for the network. So we just source a lot of this from the fleet. We train a neural network on those trajectories, and then the neural network predicts paths just from that data. So really what this is referred to typically is called imitation learning. We're taking human trajectories from the real world, and we're just trying to imitate how people drive in real worlds. And we can also apply the same data engine crank to all of this and make this work over time. So here's an example of path prediction going through a kind of a complicated environment. So what you're seeing here is a video. And we are overlaying the predictions of the network. So this is a path that the network would follow in green. And yeah.
I mean, the crazy thing is the network is predicting paths it can't even see with incredibly high accuracy. It can't see around the corner, but it's saying the probability of that curve is extremely high. So that's the path. And it nails it. You will see that in the cars today. We're going to turn on augmented vision so you can see the lane lines and the path predictions of the cars overlaid on the video.
Yeah. There's actually more going on under the hood that you can even tell.
I mean, it's kind of scary, to be honest. Yeah.
And of course, there's a lot of details I'm skipping over. You might not want to annotate all the drivers. You might want to just imitate the better drivers. And there's many technical ways that we actually slice and dice that data. But the interesting thing here is that this prediction is actually a 3D prediction that we project back to the image here. So the path here forward is a three-dimensional thing that we're just rendering in 2D. But we know about the slope of the ground from all of this, and that's actually extremely valuable for driving. So path prediction actually is live in the fleet today, by the way. So if you're driving cloverleafs, if you're in a cloverleaf on a highway, until maybe 5 months ago or so, your car would not be able to do cloverleaf. Now it can. That's path prediction running live on your cars. We've shipped this a while ago. And today, you are going to get to experience this for traversing intersections. A large component of how we go through intersections in your drives today is all sourced from path prediction from automatic labels. So what I talked about so far is really the three key components of how we iterate on the predictions of the network and how we make it work over time. You require a large, varied, and real data set. We can really achieve that here at Tesla. And we do that through the scale of the fleet, the data engine, shipping things in shadow mode, iterating that cycle, and potentially even using fleet learning where no human annotators are harmed in the process, and just using data automatically, and we can really do that at scale. So in the next section of my talk, I'm going to especially talk about depth perception using vision only. So you might be familiar that there are at least two sensors in the car. One is vision, cameras, just getting pixels, and the other is LiDAR that there are a lot of companies also use. And LiDAR gives you these point measurements of distance around you. Now, one thing I'd like to point out, first of all, is you all came here, you drove here, many of you, and you used your neural net and vision. You were not shooting lasers out of your eyes, and you still ended up here.
We might have.
So things went well.
Can't speak for everyone.
So clearly, the human neural net derives distance and all the measurements and the 3D understanding of the world just from vision. It actually uses multiple cues to do so. I'll just briefly go over some of them, just to give you a sense of roughly what's going on inside. As an example, we have two eyes pointed out, so you get two independent measurements at every single time step of the world ahead of you, and your brain stitches this information together to arrive at some depth estimation because you can triangulate any points across those two viewpoints. A lot of animals, instead, have eyes that are positioned on the sides, so they have very little overlap in their visual fields, so they will typically use structure from motion, and the idea is that they bob their heads, and because of the movement, they actually get multiple observations of the world, and you can triangulate, again, depths. And even with one eye closed and completely motionless, you can still have some sense of depth perception. If you did this, I don't think you would notice me coming 2 meters towards you or 100 meters back, and that's because there are a lot of very strong monocular cues that your brain also takes into account. This is an example of a pretty common visual illusion where you have, these two blue bars are identical, but your brain, the way it stitches up this scene, is it just expects one of them to be larger than the other because of the vanishing lines of this image. So your brain does a lot of this automatically. And neural nets, artificial neural nets can as well. So let me give you 3 examples of how you can arrive at depth perception from vision alone. A classical approach and 2 that rely on neural networks. So here's a video going down, I think this is San Francisco, of a Tesla. So these are our cameras, our sensing, and we're looking at I'm only showing the main camera, but all the cameras are turned on, the 8 cameras of the Autopilot. And if you just have this 6-second clip, what you can do is you can stitch up this environment in 3D using multi-view stereo techniques. So this is supposed to be a video. Is it not a video? Oh, I know it's a video. There we go. So this is the 3D reconstruction of those 6 seconds of that car driving through that path. And you can see that this information is very well recoverable from just videos. And roughly that's through process of triangulation and, as I mentioned, multi-view stereo. And we've applied similar techniques, slightly more sparse and approximate, also in the car. So it's remarkable. All that information is really there in the sensor, and just a matter of extracting it. The other project that I want to briefly talk about is, as I mentioned, there's nothing about neural network. Neural networks are very powerful visual recognition engines. And if you want them to predict depth, then you need to, for example, look for labels of depth, and then they can actually do that extremely well. So there's nothing limiting networks from predicting this molecular depth except for labeled data. So one example project that we've actually looked at internally is we use the forward-facing radar, which is shown in blue, and that radar is looking out and measuring depths of objects, and we use that radar to annotate what vision is seeing, the bounding boxes that come out of the neural networks. So instead of human annotators telling you, OK, this car in this bounding box is roughly 25 meters away, you can annotate that data much better using sensors. So you use sensor annotation. So as an example, radar is quite good at that distance. You can annotate that, and then you can train a neural network on it. And if you just have enough data of it, this neural network is very good at predicting those patterns. So here's an example of predictions of that. So in circles, I'm showing radar objects. And the cuboids that are coming out here are purely from vision. So the cuboids here are just coming out of vision, and the depth of those cuboids is learned via sensor annotation from the radar. So if this is working very well, then you would see that the circles in the top-down view would agree with the cuboids, and they do. And that's because neural networks are very competent at predicting depths. They can learn the different sizes of vehicles internally, and they know how big those vehicles are, and you can actually derive depth from that quite accurately. The last mechanism I will talk about very briefly is slightly more fancy and gets a bit more technical, but it is a mechanism that has recently, there's a few papers basically over the last year or two on this approach. It's called self-supervision. So what you do in a lot of these papers is you only feed raw videos into neural networks with no labels whatsoever, and you can still get neural networks to learn depth. And it's a little bit technical, so I can't go into the full details, but the idea is that the neural network predicts depth at every single frame of that video, and then there are no explicit targets that the neural network is supposed to regress to with the labels, but instead, the objective for the network is to be consistent over time. So whatever depth you predict should be consistent over the duration of that video, and the only way to be consistent is to be right. And so the neural network automatically predicts the correct depths for all the pixels, and we've reproduced some of these results internally, so this also works quite well. So in summary, people drive with vision only. No lasers are involved. This seems to work quite well. The point that I'd like to make is that visual recognition, and very powerful visual recognition, is absolutely necessary for autonomy. It's not a nice to have. Like, we must have neural networks that actually really understand the environment around you. And LiDAR points are a much less information-rich environment. So vision really understands the full details. Just a few points around are much, there's much less information in those. So as an example, on the left here, is that a plastic bag or is that a tire? A LiDAR might just give you a few points on that, but vision can tell you which one of those two is true, and that impacts your control. Is that person who is slightly looking backwards, are they trying to merge into your lane on the bike, or are they just going forward? In the construction sites, what do those signs say? How should I behave in this world? The entire infrastructure that we have built up for roads is all designed for human visual consumption. So all of the signs, all of the traffic lights, everything is designed for vision. And so that's where all that information is, and so you need that ability. Is that person distracted and on their phone? Are they going to walk into your lane? Those answers to all these questions are only found in vision and are necessary for level 4, level 5 autonomy. And that is the capability that we are developing at Tesla. And this is done through a combination of large-scale neural network training, through data engine and getting that to work over time, and using the power of the fleet. And so in this sense, LiDAR is really a shortcut. It sidesteps the fundamental problems, the important problem of visual recognition that is necessary for autonomy. And so it gives a false sense of progress and is ultimately a crutch. It does give like really fast demos. So if I was to summarize the my entire talk in one slide, it would be this. All of autonomy, because you want level 4, level 5 systems that can handle all the possible situations in 99.99% of the cases. And chasing some of the last few nines is going to be very tricky and very difficult, and is going to require a very powerful visual system. So I'm showing you some images of what you might encounter in any one slice of that 9. So in the beginning, you just have very simple cars going forward. Then those cars start to look a little bit funny. Then maybe you have bikes on cars. Then maybe you have cars on cars. Then maybe you start to get into really rare events like cars turned over or even cars airborne. We see a lot of things coming from the fleet. And we see them at some rate, at like a really good rate compared to all of our competitors. And so the rate of progress at which you can actually address these problems, iterate on the software, and really feed the neural networks with the right data, that rate of progress is really just proportional to how often you encounter these situations in the wild. And we encounter them significantly more frequently than anyone else, which is why we're going to do extremely well. Thank you.
Thanks.